Rain or shine, hot or cold, the weather affects us all. It's something of a British obsession, and the weather forecast is never far from our minds. Often because we want to know if we'll need an umbrella. The weather can change from dry and hot to a severe drenching in a matter of hours. But why? What makes this happen? We all know that hot air rises, and we also know that what goes up must come down. That cycle sits at the heart of our weather. The sun heats the air, it rises, cools, then falls back down to Earth, creating our weather and airflow. But it can't be that simple. If it were, we would all experience the same weather everywhere on Earth. So why is this not the case? And why do we have different and complex weather patterns? To find out, we need to look at the factors that affect the rise and fall of air. Earth is surrounded by an atmosphere made up of gases held in place by gravity. This atmosphere protects us from the harmful parts of the sun's radiation and keeps Earth warm through the greenhouse effect. Earth's atmosphere is made up of layers. At about 500 kilometers above Earth, the thermosphere acts as a protective shield, stopping harmful radiation. It's also the part of the atmosphere where the International Space Station orbits. Beneath that is the mesosphere. This is the layer where most meteors burn up before reaching Earth. Next comes the stratosphere, the layer that converts the sun's UV rays into heat. Uniquely, this layer gets warmer the higher up you go. Finally is the troposphere. At about 10 kilometers above Earth, it acts as a canopy. This is where our weather happens. As hot air rises, it hits the ceiling and spreads out, cooling, then falling back down to Earth. These cycles create the different weather we experience. The faster the air heats, the quicker it rises. So we need to understand how Earth heats up to understand these airflow cycles. It's the solar energy from the sun that heats the planet. If we think of the sunlight as individual rays, each one reaches Earth's atmosphere with the same amount of energy. However, at the poles, that energy is spread over a greater area than at the equator. On top of that, the energy has to travel further through the atmosphere at these higher latitudes. Then we have Earth's 23.5 degree tilt towards the sun, which influences where on Earth the energy is concentrated. This tilt gives us our seasons. The northern hemisphere points towards the heat source for the first half of the year, and the southern hemisphere for the second. Now look at what happens at the poles. Snow and ice, along with thick cloud cover, reflect a lot of the sun's energy back into space. This further reduces the energy that reaches the poles. In fact, at any point greater than 40 degree latitude, the outgoing heat radiation exceeds the incoming energy from the sun. Even with all these factors at play, if Earth were simply a land mass, we would still have a relatively simple weather system. The flow of air, known as circulation cells, would rise at the equator, where it is hottest, hit the ceiling of the mesosphere, then flow to the poles, where it would cool, sink, and return to the equator. This would be nature's way of balancing heat distribution and stopping the equator from getting ever hotter and the poles ever colder. But there are a couple more factors that affect this simple model. The first is our oceans. Land heats more quickly and to a higher temperature than water, but it also cools more rapidly. In contrast, the temperature of water changes far less between day and night and from season to season. All these fluctuations in heating and cooling disrupt the formation of a single, simple circulation cell, and a more complex three-cell pattern starts to emerge. On either side of the equator are the Hadley cells. Next to those are the mid-latitude cells, and the polar cells sit at the top and bottom of the globe. This creates three distinct bands in each hemisphere, each with its own circulation of heating, rising, cooling and falling air. You can think of them working like gears, linked together as the air circulates at high latitudes. At the top of the troposphere, the cold airflow moves between the cells, falling back to surface between each one. This movement of air creates flows between each of the cells. Between the mid-latitude and Hadley cells are the subtropical jets, and between the mid-latitude and polar cells are the polar fronts. As the circulation cells expand and contract, these streams of air meander around the globe, changing as Earth heats and cools. The subtropical jet between the Hadley and mid-latitude cells is commonly referred to as the jet stream, a band of fast-flowing air from west to east. But it's the polar fronts that have the greatest effect on our weather. As the cells expand and contract, the polar front moves north and south. Behind the polar front is colder air, and as it pushes south, we experience more unsettled weather. Being on the cold side of the polar front can lead to some of the extremely wet weather we experience, even in summer. The meeting points of the circulation cells create prevailing conditions. Where the cells come together, the air is either rising or falling. This creates constant areas of either high or low pressure. Cooler, falling air creates areas of high pressure. Warmer, rising air creates areas of low pressure. At surface level, which is what we care about, we can see from the circulation cells that the air flows from high pressure areas to low pressure areas. Low pressure areas are regions of rising warm air. As this warm air rises, it carries moisture from Earth's surface, which forms clouds and ultimately falls as rain. High pressure areas are cool, dry air sinking back down to Earth. High pressure areas are considered to bring good weather. Earlier, I mentioned that there were a couple more factors we had to consider, but so far we've only talked about one. The other is that while all this weather is happening in the atmosphere around Earth, at surface level we're rotating underneath it. Let's look at how this affects everything that is going on. One of the easiest ways to picture it is by throwing a ball. When thrown, it moves in a straight line. But if we throw the same ball from the same position while Earth is spinning, the ball appears to travel in an arc. This apparent bend is known as the Coriolis effect. This effect is also influenced by speed. If we mark a couple of spots on Earth, we can see that Earth's rotation has a bigger impact at the equator. the further north or south you move, the slower the surface is moving underneath the atmosphere. If we bring back the high and low pressure bands formed by the circulation cells, then add the flows at surface level, with air moving from areas of high pressure to areas of low pressure, and then introduce the rotation of Earth, we can see how this affects our experience of wind at the surface. This is the Coriolis effect. It explains why we have prevailing conditions. The easterlies in the middle of Earth, known as the trade winds, westerlies spanning the mid-latitude cells, and easterlies at the poles. If we go back to a flat map, we can also see how the prevailing conditions created by the circulation cells have a strong impact on our climate. While the bands of low and high pressure expand and contract over time, they stay relatively constant in the parts of the globe they cover. It's no coincidence that most of the planet's rainforests sit between the Hadley cells near the equator, where the prevailing low pressure brings frequent rainfall. Most of the world's deserts, including both poles, lie in bands of high pressure, where it is generally very dry. So what does this mean for us? It's the constant movement, heating, cooling, rebalancing and drive towards equilibrium that causes the weather we experience, both globally and locally. Although it is a complex chain of events, there are some constants that help us to understand how the weather will affect us. While many factors are in play, at the heart of everything is the sun heating the planet. This is what drives all our weather. Wherever we are, areas of high pressure are zones of falling, cooler, more stable air. Areas of low pressure are zones of warm, rising air, carrying moisture and creating more unstable weather. We also know that at surface level, air flows from areas of high pressure to areas of low pressure. We know this as wind. Knowing these key points will help us understand and interpret weather forecasts and the weather that we're experiencing much more clearly.